Hello everybody, this is Tom Skoglund. I'm going to give you a little overview of one of the new features we have in OpenMP 5.1, the Interop construct. This is really a new attempt at adding greater interoperability between OpenMP and other parallel and heterogeneous computing frameworks, and it's a new construct that enables that attempt as well. The construct provides a mechanism to request low-level information from OpenMP runtimes, to write portable, fully asynchronous code that uses both OpenMP and native functionality together, and provides us with a place to build new interoperability features as we go forward. And this all sounds kind of vague. Some of the concrete uses we have already in 5.1 are the interop types target sync, which is a way to access a synchronization object from the foreign runtime system and connect the OpenMP task graph with the task graph of the foreign runtime system. A concrete example of this would be if you're mixing, say, Sickle in OpenMP or CUDA in OpenMP, and you need a queue or a stream to be able to do asynchronous compute in the foreign system. You can get that out of OpenMP. You can have asynchronous OpenMP target regions and asynchronous CUDA or Sickle code and interconnect them correctly with dependencies without having to block your thread waiting on the host and put bubbles in your asynchronous compute pipeline. Target is a way to get native handles or foreign runtime handles to resources associated with a device. So sometimes if you're doing especially lower level stuff with a foreign runtime system, you may need access to a device handle, a context handle, a platform handle, things like that. And this is a way that you can get some of that information so that you can query properties or set things on your device. So as a quick example, this is a kind of hello world example for getting a stream with the target sync interop type. Now, clearly this is not a tiny amount of code. This is not something that you just strike out in one line and it's done. It is relatively complicated and it's pretty verbose. But the reason for this is the OpenMP tasking model allows you to mix device and host code arbitrarily. You can have a host task depending on a device task and vice versa arbitrarily, and you don't have to think about it. Now that's great for OpenMP code, but it means that whenever we want to interact with the outside world, in this case, a foreign runtime CUDA, in this example, we have to do some special, pretty careful work to make sure that that task graph gets treated correctly and we interconnect everything the way we need to. Now, the way that this is going to work is we have a declared interop object. We initialize it with the interop init target sync. We give it a dependency. And this tells the system that we need a target sync object for whatever kind of foreign runtime system exists on this device. It should be, a reference to it should be placed into our interop object, and this dependence needs to be enforced. But this is a very special kind of dependence, right? So in this case, it will block here until anything waiting on that this dependence depends on is complete. Then you can get the interop property out. In this case, you're getting the foreign runtime ID. You make sure that it's CUDA. You get the interop property that is the target sync object, which in this case we're casting off to a CUDA stream. Set the stream into cuBLOS, say, and then go do some asynchronous work in cuBLOS. Destroy the interop object, and then this waits on the CUDA stream that is referenced in the target sync object so that dependencies on R respect that dependence on the CUDA code. Now, there are only a few things you can do with this right now. You can get the foreign runtime ID or name. These are ways that you can tell what kind of foreign runtime system you're talking to. You can get the vendor ID or name. Again, it's a way to tell what it is you're working with. You might have a compiler or runtime system written by, say, IBM for a system backed by CUDA. The device number lets you just track what device the thing came from. Platform, device, device context are all foreign runtime properties that give you access to lower level information about that foreign runtime system. Chances are, if you don't know what these are in your foreign runtime system, you probably don't need them, but they're available for the times when you absolutely need to know something, like you may want to query runtime system available information like the number of compute units on a device, for example. Or to be able to use some of the allocation routines in some of the foreign runtime systems you might have. You may need one of these. Last is the target sync object. We already saw an example for this. That is a stream or a queue or maybe even a TBB group. It's some kind of synchronization object that you can use to access that native system and interact with it and have it work correctly with your OpenMP task graph. Now, I mentioned earlier that you can get fully asynchronous dependencies, and that's really how we got started on this feature in the first place, is we had people coming to us and saying, we want to be able to do things asynchronously. Well, you can do that entirely within OpenMP with target, no wait, and tasks, and it just works. But as soon as you need to go out of OpenMP and touch CUDA or HIP or SYCL or what have you, all of a sudden the only way to get this done was to completely block one side before starting the other, and vice versa. So when we designed Interop, we made it so that if you do no wait on, say, a target region, then you have interop in it, and you put no wait on the interop. This has a special meaning. It means that the target sync property inside this interop object, if you ensure that your foreign runtime system depends on the work that has been enqueued in this thing, it will respect this dependency that you have placed on the construct. And then you can use that, you go on, you destroy it, again with a no wait, and then you have a target also with a no wait. This means the encountering thread, the thread that's going through and queuing all this stuff, never blocks either side, at least as far as the model is concerned. An implementation may still decide to block it in interop in some cases if it has to for correctness. But if you're enqueuing only work that ends up on the foreign runtime system, and that system has a way to asynchronously handle dependencies, this will stay completely asynchronous all the way through. Now, going forward, we're hoping that Interop will give us a way to expose more things that will let you do more with a native system, so that when you have to optimize and reach through OpenMP, or you have some library that you need to use that can't work through OpenMP for whatever reason, that you can do that. And some of the things that we've been discussing in that direction are the ability to get information about threads, say a POSIX thread T or a std thread object, so you can actually look at your thread IDs or things like that as far as the native system is concerned. A way to access similar things for locks. You could actually pull out the implementation of a lock and manipulate it directly. That one's much more complicated. We're still working on it. And one that very recently came up is a way to query how the system maps concepts from the foreign runtime system to OpenMP's semantics. For example, in some cases, when you do an allocation for a target, you may be getting a handle rather than an actual pointer on the host if you're using the OpenMP APIs. And we're considering having a way to request through Interop what kind of handle it is that you get when you do that. If it's actually a pointer, if it's pinned memory, if it's device memory, or if it's, say, a CLMEM or a sickle buffer object. Any of these are potentially valid depending on how things are set up, so having some way to inquire about that seems useful. But hopefully you're excited about this new feature and what we may be able to do with it. If you're interested or have ideas for what we might do, maybe take some time and get in contact with us. We always love to hear from people. Thanks a lot, and I hope you enjoyed this talk. Bye-bye.